Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Today, inshallah, we are starting a new session 14, which is talking about prediction. In this course, we will talk about two kinds of predictions. The first one is the one that we studied in the previous session, which is classification. Classification was about predicting categorical outcomes. For example, if a patient is healthy or has a disease, if the image has a car or pedestrian, or if a given news article is real or fake. So we make predictions among categorical outcomes. And by the way, it doesn't have to be two outcomes only, it can be more than two. The other type of prediction that we will inshallah study in this session is called regression. And the regression is about predicting numerical outcomes. Notice that here in classification we were talking about categorical outcomes. Here we are talking about numerical outcomes. For example, how tall will this child be given that we know how tall his parents are? Or how much could this house cost given some attributes of the house like number of rooms or the area of the house? Or what temperature could it be tomorrow given the history of temperatures of this city or town? Now, in the context of prediction, what kind of questions we can ask? Let's see that on a demo. So in this lecture, we'll start with a dataset about hybrid cars. In this dataset, we have a raw pair car in which we have the model, the year of manufacturing this car, the retail price, the suggested retail price for that car, the acceleration of the car, the mileage per gallon, which is an indication of how efficient the car is, and the class of the car. Now let's look at different attributes of the cars and see if there is any association between them. So we will plot the scatter plot between the acceleration and the cost or the price of the car, and you might guess if there is a relationship between how high or how big the acceleration is and the retail price of the car. So if we look at the plot here, remember here we have more about 100 maybe 50 cars, models of cars. So you will see that there is a relationship between the acceleration and the retail price, and it seems like it is a positive relationship because on general, as the acceleration increases, the retail price increases, and that's logical. As the capabilities of the car of running faster increases, the retail price of the car will increase. Now let's look at the mileage per gallon and the retail price, or how efficient the car is and the retail price. So here is the scatter plot between the economy of the car, the fuel economy of the car, or how efficient it is, and the retail price. Here it seems like the relationship is different from the relationship that we saw here. It seems like here the relationship is negative. As the efficiency of the car increases, the retail price decreases. And that's kind of surprising, because we might think that if the car is efficient, if it is running for large number of miles per gallon, that means that the price will be higher or should be higher. But if we plot the relationship between the efficiency and the acceleration, I think that will give us a clue about why we see this relationship here. So if we plot the relationship between how efficient the car is and the acceleration, you'll see that it is also negative. So as the mileage per gallon increases, the acceleration decreases. Okay, or actually we can see it maybe easier the other way around. If the car run faster over time, the mileage per gallon will be less because it burns more oil. So that's why we have here this relationship. And of course, as it goes faster, the price will go up. That means that if it runs faster, it will be less efficient, but of course the retail price will be higher. Now, if we focus only on one type of the cars, which is SUV, Here we will just look into the SUV cars. Let's see if we will have similar or as strong as relationships as we saw in the entire dataset. So if we plot the relationship between the mileage per gallon or efficiency and the retail price, we still see it negative, but let's compare the same relationship with the entire dataset. So look at both figures here, or both plots. You will see that the relationship here is more linear. Okay, it's more linear. Here there is a relationship, of course, but it seems like it's non-linear. It is kind of curvy here. Okay, so the relationship is a curve more than it is a line here. So that brings us to a question on how we can quantify the association between two variables. So there must be a way to say that the association is strong or weak. The association is positive or negative. So let's get back to the slides and summarize the questions that we can ask so far. So one question is there any association between the variables? Is the association positive or negative? And how strong could that association be? How strong or weak is this association? So that's one kind of questions. Another kind of questions is what's the best way to summarize the data? Can we fit the data to a line, as we saw in the SUV example, although that's not, it doesn't fit very well aligned, but it's kind of a line relationship or linear relationship. Or we can summarize it by a curve. Another kind of questions that we didn't talk about yet is the prediction of new values or existing values. So if we get back here, if I am given a specific value of the mileage per gallon, can I predict the retail price? Or if I am given the height of the parents, can I predict the height of the child? So that kind of questions is also very important, and inshallah we will cover in this session. So in this session, inshallah, we will cover 4 topics all around regression. So we'll start inshallah today with association and correlation. Next lecture we will talk about linear regression. The following lecture we will cover least squares, which is about finding the best line that can summarize a data set. And the following one we'll talk about residuals. In the following session, we will continue talking about regression, but we'll talk about regression inference. So today, inshallah, we'll focus on correlation and in particular, correlation coefficient. So correlation coefficient is a number that measures how strong the linear association or linear relationship between two variables is. So if we have two variables, the correlation coefficient will give us an indication of how strong the linear association between them. And that's inshallah what we will see in this lecture. The correlation coefficient is based on standard units. Recall that the standard units is computed by subtracting the average from each point and dividing by the standard deviation. So before we compute the correlation coefficient between two variables, we have to convert them into standard units. So if we have two variables here, x and y, we have to convert x into standard units and y also into standard units. The correlation coefficient is a number that is between -1 and 1. So if the correlation coefficient between two variables is 1, that means that their scatter is perfect straight line sloping up. If it's -1, then it is exactly the same like 1. It is perfectly straight line, but it is sloping down. If it's 0, that means that there is no linear association between the two variables, or in this case we can say that the two variables are uncorrelated. Let's see a demo on how we can compute the correlation coefficient and see examples of correlation between different pairs of variables. We will start with the function of standard units that we saw before. Given an array of numbers, we convert this array into standard units by subtracting the average of each value, by subtracting the average from each value, and then we divide by the standard deviation of the entire set of numbers. So that's the standard units function. Now let's again see the scatter plot of the efficiency of the car with the retail price of SUV cars, and apply the conversion to standard units and see if the association or the pattern that we see here will change or not. So we'll convert all the values to standard units, we'll convert the efficiency, and we'll convert the retail price, we'll put them in a table, and then we plot the scattered points of the two variables. As you see here, if you look at these two plots, this is in original scales, and this is in the standard unit scale. You'll see that with standard units, of course, it is around 0 here and 0 there. And you will see that the pattern is still the same. Okay, although the scales are different now, but the association or the relationship will look like the same. Now let's continue on how we calculate R, or the correlation coefficient. By the way, the correlation coefficient is sometimes just called correlation. Okay, so when you hear someone saying the correlation between the two variables is that number, that means that he or she means the correlation coefficient. So now let's see how we compute the correlation coefficient on a simpler example first. So let's say that we have two variables, x and y, and we have the values of x between 1 and 7 and these specific values of y. So this is the data set that we will start with, and here is how it looks like when we see the scatter plot. Okay, so looking at these 6 points, it seems like there is positive association between x and y. So the first step in computing the correlation coefficient is to convert the values into standard units. So we'll do that, and we put them into a table. Now we have the original values of x and y, and the values of x and y after converting to standard units. Now let's look at them in a scatter plot. As we saw before, they are very, very similar to the original plot, but now they are in standard units. The next step in computing the correlation coefficient is to multiply the corresponding values. Okay, so x standard unit vector is the values of x after conversion to standard units, and similar to y standard unit vector. So when we multiply the two vectors, actually we are multiplying element-wise. So this is the product element-wise between x and y in standard units. Now the correlation coefficient will be the average of those values. So let's add the product to the table. So that's the product of every point here. Now we'll take the average of these products, and that will be the correlation coefficient. Okay, so the correlation coefficient here is 0.6. Now the rationale behind how we calculated the correlation coefficient is beyond the scope of the course, but it is sufficient for now is to know that the correlation coefficient is computed that way. We convert the values into standard units, then we do the multiplication element-wise, and we take the average of the multiplications. So we will get a number between -1 and 1, as we said earlier. The number here is 0.6, which means that the correlation is positive, but it is not perfectly a linear association. Okay, so as we see here, it is not perfectly line, it is not perfectly linear, otherwise we would see these 2 points somewhere here, but it's still positive. Okay, so correlation coefficient actually measures how strong or how tight the cluster of the points around a line. Okay, how tight the cluster of the points around a line. Okay, so the value here is 0.6. That means that it is positive, but it is not, of course, perfect. Let's capture all of what we did in one function that compute the correlation between two variables in a table. So we convert to standard units, we do the multiplication, and then we take the average. Let's test it on the same x and y values that we saw before. We will get the same number, which is 0.617. Let's apply this on the SUV plot. the correlation between the mileage per gallon and the retail price. Remember, that was kind of negative, so that's the number that we get, minus 0.66, which means that there is a good amount of association or relation, but it is negative. If we try also on the same two attributes, but in the entire data set, remember, that was a kind of curvy relationship, so we would expect that the number here will be less than that number, so the correlation here is minus 0.53. Okay, so the absolute value is less than this, so the association is less, but still it is negative as we saw before. We also had a function that was defined in the beginning of this notebook. Don't worry about how it is defined, but this function just simulates relationship between two variables given the value of the correlation coefficient between them. So here is an example of data that has -1 correlation coefficient. As we see, it is perfectly aligned, the data is perfectly aligned with a straight line, but it has a negative slope. Here it is a 0.5, so we would expect that the cluster of the points is around a line, but it is not very tight. Okay, so the relationship is still positive correlation, but it is not as tight as we see here. Let's see it in the negative side. So again, very similar to this, but the slope is negative. Here's an example of two variables when they are completely uncorrelated. You will see that the points are all over the place like that. Okay, so there is no, we cannot say that they are aligned with a line at all. Now, what happens if we switched the two variables? So if we computed the correlation between y and x instead of x and y. Here is the scatter plot when we look at x and y, and here's the correlation that we got before, 0.617. If we switched y and x and plotted the data, we will see similar association, of course. Okay, so switching x and y should not or will not change the association between the two variables, of course. And if you remember how the correlation coefficient is computed, you will see that it is symmetric. So it doesn't matter if we switched y with x. So the correlation will be also the same. So let's get back to the slides and summarize what we got so far. So the definition of the correlation coefficient is that we have two variables. We have to convert them into standard units. Then we get the product of the elements or the values in both variables, and then we get the average of the products. And this is what we call the correlation coefficient, or the R value. Again, the correlation coefficient measures how clustered the scatter is around a straight line. If the cluster is very tight around the straight line, so the correlation coefficient value will be higher. If the cluster is scattered, is not that tight around the straight line, then the correlation coefficient value will be lower. Now, when we see a correlation between two variables, we have to be very careful when we interpret the association or the relationship between the two variables. So the first thing is that the correlation is an indication of association, but it's not necessarily a causation. Okay? Of course, we talked about causation before, at least in 2 sessions in this course. But actually, the textbook in this chapter gives a very nice example. Let's say that we had a study on students in a specific school, and we measured the mathematical skills of the students and also their weight. Okay? And we found that there is a positive correlation between the weight of the student and the mathematical skills of the student, or how good the student is in math. Of course, that doesn't mean that if you gain more weight, your mathematical skills will go up, or if you try to improve your mathematical skills, you will get more weight. There is of course a confounding factor here, which is the age of the student. In general, or on average, when the student gets older, he gains more weight and his or her mathematical skills will improve. So we cannot say that the relationship here means causation. There are three other important issues that we want to talk about: nonlinearity, outliers, and ecological correlations. We'll do that through a demo. So let's get back to the code. First thing, we want to make sure that we understand that correlation means linear association. So sometimes the association between two variables is very strong, but it is non-linear association or non-linear relationship. So for example, if we have two variables in which one of them is the quadratic value of the other, so we have x and x squared. So we have x and x squared. So this is the relationship. Of course, the relationship here is very strong, but it is quadratic. It is non-linear. Now, what could be the correlation coefficient value or the correlation between these two variables? We might think that it should be strong, but remember that correlation coefficient means linear association. So in fact, the correlation between these two variables is zero. Okay, is zero because the relationship between them is not linear. So zero correlation doesn't mean that there is no association at all between the two variables. There might be another association, but it is not linear. Another thing is the outliers. The correlation coefficient or correlation is very sensitive to outliers. So if we have a data set like that, which is perfectly aligned here, the correlation of course of this data set will be very high, which you would expect that it is 1 actually, because it is perfectly aligned. It's 1, 1, 2, 2, 3, 3, and 4, 4. So it is perfectly aligned with a straight line. Now let's say that we added one more point, which is 5, 0 here. So we added a point somewhere here. Will that affect the correlation coefficient? Of course, the answer is yes. But how much will the correlation coefficient be affected? So if we compute the correlation in this case, we will get 0. So you see how severe the correlation will be if we just added one outlier. So it is very sensitive to outliers. If we see another example, if we added another point, which is 3 and minus 2 to the original set of points, we will get this scatter. Now, will that be as severe as this? Let's see. The correlation here will be 0.57. So it's much less than 1, which is the original data set, but still affected negatively by adding this outlier. But it was not like adding an outlier here. So that means that the correlation is really sensitive to outliers. The last point in our lecture is about ecological correlations. What we mean by ecological correlation is that correlation that is between aggregates or averages. So let's look at another data set that is measuring the skills or the scores of students in US states in the SAT exam. Okay, so we are measuring actually different scores in different parts of the exam: critical reading, math, and writing, and that's the average score of students in that state. Okay, now we want to see if there is a correlation between critical reading and the math score. So if we plot the relationship, or if we plot the scatter plot between the critical reading and math, we will get something like this. So this is clearly a linear correlation, a linear line, which means that we will get a high correlation coefficient value. So let's compute it. We get 0.98. So that's very high. That's very close to 1, which means that there is strong correlation between critical reading and math. But remember, the relationship here is between the average critical reading of students in a state and the average math score for these students in the same state. So the relationship here is between averages. So actually every point here, so for example this point, is an average of so many points with the number of students in that state. If we actually plot the scores of the actual students, not the average score, we will see that the scores of the students will be scattered around this point, okay, for both the critical reading and the math. So if we plot the scores of all students in all states, it will be more fuzzier than this plot, and thus the correlation will be actually less in this case. So we cannot say that generally for all students this is the correlation between the critical reading and math, but this is on average. Okay, so this is the correlation between average scores. So the actual correlation might be less than that. So we have to be really careful in these three things: the ecological correlation, and the when we have outliers in the data set, and also when we interpret correlation, we have to make sure that we understand it is about linear relationship, not any other relationship. We'll end this lecture with two more slides. One will be discussed inshallah in the online session. I want you to check for these 4 pairs. For each pair, I want you to determine which one will have a higher value of R. So in each pair here, which of these two data sets will have, or two relationships will have higher correlation coefficients. The last thing is a paper that is linked from the textbook. That paper was published in a reputable journal, and it says that there is a relationship, or there is a correlation between chocolate consumption in a country and the number of people who got Nobel Prize in that country. So it says that there is a positive correlation between these two. If you consume chocolate more in that country, there is a higher chance that you will get a Nobel Prize. Of course, this is very controversial. Look at the textbook, see the paper, it is very short, it's just 2 pages. Read it, and also read discussions about the paper. Well, that will end this lecture. Inshallah, we'll continue this session in the next lecture. Assalamu alaikum wa rahmatullahi wa barakatuh.